Okay, again. So last time we saw inverses, and we spoke about two different ways to find an inverse, right? The row reduction way and the adjoint method. Did we actually use the inverse to solve a system? I don't remember.
No.
No.
No. You didn't do it.
Okay, well, it's not gonna, it's just matrix
Oh yeah, you
multiplication.
did. Never mind. You
Did I?
Yeah. You did.
So, we know that if AX equals B and A inverse exists, then you can actually solve the system and it's going to be X equals A inverse times B. Right, so if you find the inverse, you can do the multiplication. I don't remember if you actually did.
You gave us a formula. Yeah.
I know we definitely found this guy, but I don't know if you used it to solve
Yeah,
it.
we did.
Yeah.
So I believe, let's go over an example. So we were looking at this system. Let's do a quick look at it just in case. And so the coefficient matrix of this system was A is equal to 1 minus 2, 3, 2 minus 1, minus 1, minus 3, 1, 4. Alright, and we saw two things. We saw that the determinant of A was equal to 4, and we found A inverse was this guy. Minus 3 over 4, 11 over 4, 5 over 4, minus 5 over 4, 13 over 4, 7 over 4, minus 1 over 4, 5 over 4, 3 over 4. And so, one thing you could say here is that once you find that, this would imply that your x, y, z would be equal to A inverse times the constant matrix over here. Or in other words, that's going to be that matrix, minus 0, 4, 11 over 4, 5 over 4. This 5 over 4, 13 over 4, 7 over 4, and 1 over 4, 5 over 4, 0 over 4. And so the answer would actually be minus 3/4, minus 5/4, minus 1/4. Would actually be the solution to the system. So a problem like this is very common for the final. I'll definitely ask you about something like this on the test. So I'll say something like, let A be this matrix, find its inverse. And you'll do whichever method you want. I don't care which method you use, but ultimately you'll get here. And then there'll be a part B that says, use your answer in part A to solve the system, blah. And then you're going to recognize that, oh, the matrix that you have to find the inverse of was the coefficient matrix of blah. And then all you have to do is do this multiplication, and that's actually your answer. So we know that the inverse exists, means the determinant is not 0. Determinant is not 0 means we're guaranteed to have a unique solution. And in a square system, the unique solution is given by A inverse times B. And the answer is, we just multiply both sides by A inverse. By definition, A inverse times A is the identity, so I'm just left with X on this side, and on that side, I have the answer. So that was the idea. So I'll just mention that you will need to be able to find the inverse of a matrix. It's usually going to be a 3 by 3 and use it to solve a system. many uses of the inverse, but that's the use that we'll use for it. Pretty much the only things we're doing in linear algebra are the things that help us to solve systems. So we don't really care about anything else, which is, it's not what linear algebra is about, but that's kind of what we care about. So we learned about row reduction because it helps us solve systems. We learned about finding inverses because it helps us solve systems. And the next thing that we're going to look at today is called eigenvalues and eigenvectors, and we're going to apply that to solving systems. But yeah, that was the basic idea behind inverses. So we can end there and move on to eigenvalues and eigenvectors. Which I believe is chapter 7. Now there are many uses of eigenvalues and eigenvectors, but again, we'll be looking at it from a very narrow point of view. And it's probably best to introduce these guys in terms of a geometrical context, but we didn't really do any geometry. We never really spoke about what it means to multiply by a matrix. What does that mean geometrically? But the idea is you can actually transform vectors. You can think of matrices as linear transformations. I told you that they're functions, but you can think of them as, they're called linear transformations because what they do is they can translate things in the plane. So you can have a matrix that deals with projections, for example. So you multiply a vector by, so for example, if you take A equals 1, 0, 0, 1, right? This you can think of it as a 2 by 2 matrix, but geometrically what it is, it's the matrix that if you multiply any vector in R2, it projects it to the x-axis, right? So we not only think of it as a matrix, we think of it as some sort of operation that can happen geometrically. So you'll realize that if you multiply this by x comma y, like a vector xy in R2, the result would be what? It would be x comma 0. It will actually kill the y coordinate, right? So you can think of matrices in terms of what they do geometrically. So I can have my random vector here, x comma y, but multiplying by this matrix, what that does is it projects it down to the x-axis. And this new vector, I can think of it as a times x, right? And I can do that for any vector in the plane, and multiplying by this matrix, all that it's going to do is going to map that vector to the x-axis, do a vector projection to the x-axis. Okay? So that's a very useful thing with matrices. That's ultimately where you'd want to go, and you can get a lot out of studying things in that context, but we're not going to do it. But I just want to sort of introduce that to you in context. Now, sometimes, let's actually illustrate, let's kind of segue into eigenvalues and eigenvectors here. What if my matrix was already along the x-axis? What would multiplying this guy by this guy do? Nothing. It wouldn't do anything. It would leave that vector alone. Other vectors that are hovering all over the place, not on the x-axis, it's going to take them and bring them down to the x-axis. Notice that guys along the x-axis, it's not going to do anything. What about if I took this matrix? What would that do to a matrix that's lying along the x-axis?
Increase it.
Right. It's not going to change its direction. It's just going to scale the vector, right? It's going to make the vector longer. Right? Now, vectors that have this property, that when you take a certain matrix and you multiply it by them, if it does not change their direction, but at most what it does is it scales the vector, right? These vectors are important for a multitude of reasons. We're not going to see all the multitude of reasons, but such a vector is called an eigenvector of this matrix, right? So whenever we multiply a vector by a matrix, if what that does is nothing but scale the vector, we call that vector an eigenvector. And the value that it is scaled by, in this case it increases its length by 2, that scalar value that we scale the vector by is called the eigenvalue. Okay? Now, it's very important that we are able to find these guys because of one of the contexts that we're going to do in this class, but this is actually, in general, a good problem to be able to solve. Right, so our matrices have a geometrical interpretation. Multiplying a vector by a matrix is performing some sort of transformation in the plane. Could be a rotation, a projection, a stretching, a shrinking, something like that. A shear. Right? But if you multiply a vector by a matrix and all that happens is the vector is scaled, we call that vector an eigenvector, and the scalar value, we call it its eigenvalue. So that's what we're going to look at here, eigenvalues and eigenvectors. And with that intro, I think I can just write down the definitions and you'll be able to make sense of them. Let A be a square matrix. By the way, you can think of this as mapping, it could be like n by n. You can think of this as some sort of transformation that takes n-dimensional vectors and outputs n-dimensional vectors. Right? So it's going to be a square, so you're doing something in the plane or something in 3 space or something in 4 space, and you're maintaining the dimensions that you're working with. Right? So let it be a square matrix, then the set of non-zero vectors for which a times x equals some scalar times x. That's the Greek letter lambda. That's the typical thing that we use. Or some scalar lambda. Right? So the set of non-zero vectors for which this is true, multiplying the vector by the matrix only scales the vector. Are called the eigenvectors. The scalar lambda corresponding to each such vector. It is important to be able to find such vectors and scalars for a given matrix. And so now I'm going to show you how we're going to do that. So you take some linear transformation, which you can describe as a matrix, multiply that by a vector. If it is the case that that vector is only scaled by that linear transformation, we call it an eigenvector. Of course, 0 is always going to be a solution to this equation, so we only care about the non-zero ones because 0 is kind of stupid. Right? 0 is the one that, okay, the 0 vector, what are you going to do with that? Right? That's the guy that points everywhere and nowhere, not very useful. But if there's a non-zero vector for which this is true, it's something that we're going to want to know about. For various reasons. So let me show you how we're going to find it. Note, if ax equals lambda x, this means I can actually subtract ax from both sides. Get the 0 vector. I can then use a property of matrices to factor the x out. stays on the right side because matrix multiplication is not commutative in general. So this is a scalar, so it won't make sense for me to just write it by itself. So it's customary that if we want to represent a scalar equation in a matrix, we multiply it by the identity to give it a matrix form. Okay? So we'll have this equation. Note, obviously 0 is a solution, but we want other solutions. It means that we want this system to have more than one solution. So we don't want a unique solution. How do we ensure that we don't have a unique solution, just 0 by itself? Right. Think of a usual system, ax equals b. How can you guarantee that that does not have a unique solution?
Determinant?
Determinant? What can you say about the determinant?
It doesn't have a determinant.
When would it have a unique solution in terms of determinant, if your matrix is squared?
It has it.
If the determinant of A is not 0?
If the determinant A is not 0, you have a unique solution. We don't want a unique solution, so what we're going to do is we're going to make the determinant 0. We want then the determinant of the coefficient matrix must be 0. Because that forces us into a situation where we do not have a unique solution. So 0 is not going to be our only solution in general. And as long as that system is solvable, we can find our eigenvalues and eigenvectors.
Does it matter which is first, the
No.
lambda I or the A?
No. Because ultimately, when you take a determinant, you're going to get some scalar value. It's going to be an equation where you can multiply both sides by -1. It's not going to matter who you put first in the journey. So that means this is what we want. So this is an important equation. It's called the characteristic equation of A. Which might sound familiar to some of you who've taken differential equations, and that's not an accident, by the way. In fact, we're going to use this to solve systems of differential equations. That's the input. So that's called the characteristic equation for the matrix. So the idea is, here's how we can find our eigenvalues and eigenvectors. The lambda solutions to this equation gives us the eigenvalues. Solutions for, let me actually number the equations. 2 equation 2 gives us that. I'm going to call this equation 1, that equation 2. So this is an important equation. From that I can get to this. So here I'm just going to have a scalar equation. It's going to be some, in fact, it's going to be a polynomial when I get here. Right? This is going to be some polynomial equal to 0. You're going to find the roots. Once you find the solutions for lambda, those are the eigenvalues. You're going to take each of those values, plug it back into here, and solve for the vectors, and that's going to give you the eigenvectors. So that's the procedure. It's actually a 2-step procedure. We always start by finding the eigenvalues first, and then we're going to find the eigenvectors. So let me do an example. Let A equals this matrix. -5, 2, 2, -2. You're always going to be asked about a 2 by 2 matrix. They're never going to give you anything bigger. Find its eigenvalues and corresponding eigenvalues. So let's see how we do this. So that'll be a part of a question that you're going to have to answer. So first, what we're going to do is we're going to find the lambdas, if there are more than one. We're going to solve the determinant of lambda I minus a equals 0. So that means the determinant of lambda I is just going to be, of course, the identity matrix times lambda minus the A. And set that equal to 0. This is going to mean that I'm going to find the determinant of this matrix. Lambda plus 5 minus 2 minus 2 lambda plus 2. By the way, it's okay if you just jump to this step. Just realize that you're going to take lambda minus this, lambda minus that, and negative of those. You can just remember that and jump to this step. But ultimately, this is the equation we want to solve. So what is going to be the determinant of that? It's a 2 by 2. So this times this minus this times that. So this is called the characteristic polynomial. That's what this guy's called. So, but now it's just an equation that we can solve for lambda. Lambda is just a variable in this equation. It's a quadratic equation, so hopefully you remember how to solve quadratic equations. Why we gotta know how to solve quadratic equations? Okay, so we have lambda squared plus 7 lambda. She's never here. When it's important, equals 0. So this is just lambda squared plus 7 lambda plus 6 equals 0. Can we solve that? Can we factor? We'll usually be able to factor. It's not going to be very nice if they don't know how to factor. 6 and 1 plus and plus. So I have lambda 1 equals minus 6. Lambda 2 equals minus 1. These guys are your eigenvalues, right? This matrix has 2 eigenvalues. So we found the eigenvalues for this matrix. Now let's find the eigenvectors. 2. So we want lambda I minus a times x to be 0, and we're going to want to solve that system for each by plugging in each of these lambdas. So in the first case, when I'm doing lambda 1 equals 6, negative 6, I'm going to plug that in. So this means I want, so what's my matrix going to look like? I'm going to plug in negative 6 here, right? And that's going to be my matrix. That means I want minus 1, minus 2, minus 2, minus 4. I'm going to solve that system for 0. Now we have a system of equations that we want to solve. It's homogeneous, definitely has a solution. 1, 2, 0, just take row 1 times minus 1. And if I take, how would I get yellow? or if I do minus 2 times row 1 plus row 2, what would I get? Minus 2 times this is plus 2 plus that, 0. Minus 2 times this is plus 4 plus that, 0. 0. So this means, if I look at this as my x1 column and my x2 column, my x2 is equal to t, and then row 1 tells me that my x1 is equal to minus 2t, which means my x1, x2 is equal to t times minus 2, 1. And this guy here is the corresponding eigenvector. It's the eigenvector corresponding to lambda 1 equals minus 6. It means any vector in your plane that is this guy, or a scalar multiple of this guy, multiplying by the original matrix is going to stretch it by a factor of negative 6.
What is that at the bottom?
What?
The last. Under. What is it?
But this is row 1,
Oh.
colon. So remember we identified the guy that doesn't have a pivot, x2 does not have a pivot, so he gets to be a parameter. Then we start reading on the rows. Row 1 would tell me that x1 plus 2x2 equals 0, which means x1 is minus 2x2. So I get x1 is minus 2t, and then I plug those in. Right? Factor out the t, and that's my vector. Right? All vectors that are some scalar multiple of this guy will get stretched by minus 6 when you multiply by the original matrix A. So that is the eigenvector corresponding to this eigenvalue. All vectors parallel to this get stretched by this much. And now you do it for the other one. Same idea, we're just going to solve the homogeneous system. So if lambda 2 is equal to minus 1, I'm going to plug in minus 1 into the original. What was lambda plus 5 minus 2 minus 2 lambda plus 2, right? So plug in minus 1 here. 4 minus 2 minus 2, plug in minus 1. And I'm going to solve this system. Minus 2, 1, 0. This guy here will be, let's kill that, right? So I'm going to multiply this by 2. 2 row 2 plus row 1. 2 times this plus that, 0. 2 times this plus that, 0. 2 times this plus that, 0. And by the way, you're always going to have, it's never going to actually reduce the identity because we set the determinant equal to 0. Right? So you're always going to have some sort of, you're always going to end up in the case where you have infinite solutions. And so we have, in this case, x2 equals t. I can use the same variable because it's a completely different situation. And so in row 1, I would get minus 2x1 equals minus t. So this means that x1 is t over 2. And so that gives me x1, x2 is t times 1 over 2 minus 1. And don't like fractions, so I'm just going to scale it to get something nicer. Call it r, the new scalar, where I'm replacing r with like a half t or something, and that would be 2 minus 2. 1 minus 2.
That's plus 1.
Plus 1? Where?
Let's see.
This is plus 1, yes. And that's the eigenvector corresponding to this eigenvalue. I'm going to write this, I mean it's not official notation or anything, but I'll write this as shorthand, lambda 1 vector. I'm going to call this lambda 2 vector, because you need to know who they correspond to. So all vectors parallel to this will be scaled by -1. Those are the eigenvalues and eigenvectors of the original matrix. So if you're given the matrix, which was minus 5, 2, 2, minus 2, it has two eigenvalues, which are these guys, and their corresponding eigenvectors are these guys. So all vectors in R2 that are parallel to this get scaled by minus 6. All vectors in R2 that are parallel to this will get scaled by minus 1. But literally every other vector in the plane, besides the 0 vector itself, multiplying by A is going to do something radically different. It's going to completely change their direction. Right? Only these two directions in R2 will not change based on that guy. They would always remain parallel to the original. Any questions? I mean, it's not difficult. It's something you have to get used to, but that's pretty much it. You take lambda minus the vector, find the determinant set equal to 0, you're going to get an equation that you can solve. It's going to be quadratic because you're always going to get a 2 by 2. So you'll get two values. And for each of those values, you go back into the original matrix, plug in that lambda value, solve the homogeneous system, you'll get vectors as solutions, and they correspond. Okay. So remember this, because I'm going to erase it. Copy, you done? So those are eigenvalues or eigenvectors. They're super useful things to be able to calculate, and as you can see, they're not difficult to calculate in principle. Really where difficulties come in is if your matrix that you're working with is super large, and so you have this polynomial of some really big degree, and then solving that can be a challenge. And that's where computers would come in. But in principle, this is how we find them. Here's an application. How many of you are doing differential equations? I don't know.
I'm doing it.
Not that many. So, I'm going to talk about a very specific kind of differential equation.
What's that?
Technically there could be a plus b here, but I care about the guys that don't have the constants here. But an equation of this form is called, Kakab, what's this called?
Is it a homogeneous? No. First
First order
linear.
linear differential equation.
Yes.
Okay? It might be called for emphasis, you might call it an ordinary differential equation because it just has an ordinary derivatives. When you get to multivariable, the multivariable context in this, you might have them called partial differential equations because you can take partial derivatives. But here is just a function that when I differentiate it, I get some scalar multiple of itself. That's called a first order linear differential equation. And it happens to pass through the origin. Right? They don't have to. You could have a plus in it, but we're not worried about that at the moment. So, this is called the first order linear differential equation. They're very important. Can anyone tell me an example of where such an equation might show up?
Circuits, linear circuits.
Linear circuits, something even more elementary for someone who hasn't done circuits. Like you've seen things like this in Calc 1 actually.
Population growth?
Population growth, right? This is a very basic model of population growth. It's also a very basic model that if you know, you can describe the velocity of something in terms of its first derivative and things like that. Can anyone tell me a solution to this?
Just like integrate.
E to the x.
E to the ax. Note, y equals e to the a x or t solves, we say it solves this differential equation. And of course, any constant multiple of that will also solve. So for example, if you have y prime equals 5y, then y equals c e to the 5x is actually a solution to this. What being a solution to a differential equation means, it is the function that when you plug it into the differential equation, it's true. Right? Notice that here, since if I assume that y is this, if I take y prime, that would be 5c e to the 5x, but that was your original y. So that's just 5 times your y, right? So this is called a differential equation. You don't really have to know what it is if you're not in differential equations. It's just an equation that has a derivative in it. That's a fancy way to say, here's an equation that involves the derivatives of a function and the function itself, right? Equations in this form, we call them first-order linear differential equations. To solve such a differential equation means we need to find a function so that when I take that function and plug it into this equation, it makes sense, right? To say something like y equals x squared is not a solution to this differential equation, because if I differentiate that, I do not get 5 times itself, right? So solving it means we have to find answers to this, functions that make sense in the original equation. Okay. So, sometimes such equations appear in systems. Like, for example, so you can imagine we're measuring the population of 2 populations and we're measuring their rate of change, their growth. You might end up with something like the rate of change of one population, you can express it as a constant times itself plus constant times some other population, and the rate of change of the second population is some constant times that plus another constant times that. Right? This is called a system of first-order linear differential equations. Right? Very similar to a system of differential equations, except here we have derivatives involved. Okay. And you want to solve this system. That's the point. And it turns out we can actually solve this using eigenvalues and eigenvectors. Notice as well where would this even come up? If we write this in matrix form, right? So we can, if we set, let's say y prime the vector, I can write it as y1 prime, y2 prime. I can set the matrix A to be A, B, C, D. And I can set the matrix Y to be y1, y2. Then the above system is y prime equals A times Y. Right? That's the matrix form of the above system. So I have a first-order differential equation. It's just an equation that measures the derivative of something in terms of itself. Like a population, the bigger the population, the faster it will grow. It's proportional to its rate of change is proportional to its current size. You can have 2 or more populations that you're studying together where they interplay on each other, and so you can come up with a couple or more sets of differential equations. You end up with a system of linear differential equations. We can translate that into the matrix form, pretty much using the same principles that we translated regular linear differential equations in the matrix form. And now we want to solve such a system. I want to find 2 functions, y1 and y2, that make sense when I plug them into this system. I'm going to tell you right now how to solve this. The solution to the 2 by 2 case. So this actually applies in general, but we're specifically talking about the 2 by 2 case. So I have two populations, 2 unknowns, 2 equations. Turns out we know exactly what the solution of this is going to be. Your y vector, if I want to solve this for y, is actually going to be given by C1, that's the arbitrary constant, lambda 1 vector e to the lambda 1 x for t. They usually use t when they're talking about differential. Plus C2, lambda 2 vector e to the lambda 2 x, where lambda 1, lambda 2 are the eigenvectors of A corresponding to the eigenvalues lambda 1, lambda 2 respectively. So I have a system of differential equations, something that looks like this. I can write it to look like that. And it turns out if I find the eigenvalues and eigenvectors of this guy, I can actually use that to solve this system. I can find what both functions are simultaneously, and that's what the answer is going to look like. Take the eigenvector, multiply e to the lambda 1 x. So remember, these guys here in the power, they're the scalars. These guys here are their corresponding eigenvectors. So let me sort of write down now what a full problem like this would look like and how to solve it. That a equals 5 minus 2, 2 minus 2. Minus 5. 2. 2 minus 2. Find its eigenvalues and corresponding eigenvectors. And use these to solve the system y1 prime is equal to minus 5y1 plus 2y2, and y2 prime is equal to 2y1 minus 2y2. So I have two functions, and if I take their linear combination in this form, that's actually the derivative of the first one. Their linear combination in this form is the derivative of the second. So there'll be a final like that on the test and on the final. It's always going to be a 2 by 2 system. You never get. It's very rare that they go larger than that. In principle, though, it's going to be essentially the same idea. If you see something larger, just you'd have a 3 by 3 instead of a quadratic. You have a cubic to solve. In principle, everything else is the same. But this is a very typical question. Might be phrased slightly differently, but this is going to be the gist of it. You're basically going to be asked to solve a system of linear differential equations where the coefficient matrix is just going to be a 2 by 2, and you can solve it by finding the eigenvalues and eigenvectors. We found So what you do then is you go through the whole process of finding eigenvalues and eigenvectors. And so you'll know that lambda 1 was minus 6, and lambda 1 vector was this, and lambda 2 was minus 1, lambda 2 vector was, what was this guy?
Negative 2, 1.
Negative 2, 1, this is 1, 2.
Yep.
So this means, so you go through that process. You set up the determinant of lambda I minus a equals 0, you solve for this and this, plug it back into the system, solve the homogeneous system, and you'll get this and this as the answer. And once you have that and that as the answer, you can literally now write down the answer for this system. This means that the solution vector, i.e. y1 and y2, are given by c1 times minus 2, 1, e to the minus 6x plus c2, 1, 2, e to the minus 1x. C1 and C2 are arbitrary constants.
Wait, isn't it y prime on the left?
Huh?
Wait, is it not y prime on the left?
No, I'm
Oh,
solving
yeah,
for
but
y.
Yeah, but no,
Right, so to solve a differential equation, you want to get rid of all the derivatives and just talk in terms of the original function. And that's kind of going to be the answer. Note what this means, by the way. You can write that and that will be your answer, but note what this is saying is that your y1 is going to be minus 2c1 e to the minus 6x plus c2 e to the minus x. Your y2 is going to be c1 e to the minus 6x plus 2c2 e to the minus x. So I can, this pair of functions actually satisfy the differential equation, right? Which means if I take minus 5 times this guy plus 2 times this guy, it will be the same value I would get as if I took the derivative of the first one. And the derivative of the second one is actually if I took 2 times this guy minus 2 times that guy. You can check to verify yourself, but that's actually going to be that. If you take the combination of these on the right side, you'll actually get the derivatives on the left side. It's not super common, but sometimes they might throw in what we call an initial condition. So let me show you how to deal with that. Called an initial condition. Basically, this is just information about a single point on the solution that you want. Okay? So, example, if I go back to the silly example, if I have y prime equals 5y, sometimes they might tell you, you know that the solution is going to be c e to the 5x, right? But what this guy is called, he's called the general solution. Because for different c values, you'll get another solution. Every single c value you can choose will be an answer, will solve this. But they might give you an additional information. I don't care about all of the possible functions. I want the particular function that passes through the point 0, 2. I want that specific function, right? So you have an infinite family of functions that solve this system, but you only care about one that passes through a certain point. So you can say, when the x value is 0, I want the y value to be 2. And so what you can do is, you can plug in the initial condition. And so basically you're going to plug in x equals 0. So that's c e to the 0. You're going to plug in y equals 2. And so you can solve for that and you can get c equals 2. And so what that means is that y equals 2e to the 5x. This guy here is called a particular solution. So there are two kinds of solutions that you can have when it comes to differential equations. You can have what we call a general solution, which means it tells you the entire class of functions that will work in this equation. But sometimes you want a specific one that fulfills some so-called initial condition. And all that means is just once you find the general answer, plug in those values into this, and then you can get a specific one of these infinitely many functions that solves the equation and passes through that point. Such an answer is called a particular solution. So in a similar way, we can give you a system of differential equations, and I can say I want to solve this, but I want to solve it with these specific initial values. And so, example. Solve the system y1 prime equals minus 5y1 plus 2 y2 prime equals 2y1 plus 2y2. Subject to I want this condition. At time equals 0, my y1 has value 2. And at time equals 0, my y2 has value minus 1. So we can think of the x value here as time, and I'm measuring populations and their rate of change. And I said, sure, this is the equation that we figure out these populations follow, but I know it, well, with -1 it doesn't make sense. The population idea doesn't make sense. I could put a +1, but I think fractions on the and might not be nice. But we just know that the functions I want, it will satisfy those values. So what we can do is we know the solution to this. So what was the solution to this? y1 was given by what? -2 c1 e to the minus 6x
Plus C2.
plus c2 e to the minus x. This one?
E to the negative 6x.
You mean c1 e to the negative 6x?
Plus 2C2 e to the negative x.
Okay, so what? Right, so you can get to that by finding the eigenvalues and eigenvectors. And so now what you'd have to do is, this gives you a general function, general solution, right? For all values of C1 and C2, you'll get a different answer here. But I want the specific answers that fit this criteria. And so what I can do is, I can plug in x equals 0 into the top function and set it equal to 2. So that means 2 is equal to be minus C1 plus C2. And then I can plug in x equals 0 to the second equation and set that equal to minus 1. It's going to be C1 plus 2C2. So now I have a system of equations that I can solve for C1 and C2. All the systems of equations. What I can do here is, let's say we want to, this is equation 1, that's equation 2. What we can do is just say 2 times equation 2 plus equation 1 or something like that. 2 times this plus that is 0. 2 times this plus that, 0. 2 times this plus that is 5C2. You get C2 equals 0. Which means C1 equals minus 1. And so, C1 was -1, so that's just going to be 2e to the -6x. C2 was 0. So your y2 is equal to minus e to the -6x. So there are multiple levels, but usually the first question is how it's going to be asked, well, the second question. So you're going to be given a matrix or a system, and they're going to ask you, find the eigenvalues and eigenvectors for the system. Then they're going to ask you, use this to solve this system of a differential equation. Then you're just going to plug in the values, the eigenvectors as the coefficients of the e's, and the eigenvalues go in the powers, and that's basically it. And if they give you like initial conditions, just plug them into the answers that you got, solve for the C1 and C2, and then come back and write it down. So, that's it. That's 392. That's all we need to know. I'm out of here.
Skip the first one.
Okay, so yeah, that's it. So last test is on Tuesday. Unless you guys want to do it Thursday. You want to do it Thursday? So last
You
test on
sound too
Tuesday.
excited.
Yeah.
What are you?
It's gonna be stupid easy. On Thursday, but by Thursday I should actually see what your final looks like. So if there's anything else I need to like tell you guys about, I can tell
Can
you
you let
guys
us see
about
the
that.
final?
Huh?
Can you let us see the final?
So I expect it to be a standard final, but if something is kind of off that you should be aware of, I'll let you guys know, and we'll actually stop there.
So we're gonna have like a review on Thursday?
We can have a review. So so you guys will come up with the any questions you might have in terms of. Yeah, but actually what we'll do is, if there's anything to tell you guys about the final, I'll tell you about the final. And if nothing, we'll do a little review and go over some important things.
You're gonna give back the exam on
Huh?
Thursday?
And I'll give back exam 3. Yeah.
I mean, either way, at that point, it's just